Hi, in this today's session, we will try to calculate the electric field due to a system of symmetrical charge configuration with the help of a Gauss law. So let's see the first case when you have an infinitely long straight wire with a uniform charge density. So here I am having an infinitely long straight wire which is having a uniform linear charge density, say lambda, and here let us consider this lambda to be a positive, which means that the charge available on this wire are my positive charges. Now here let me consider a origin or else a reference point of this wire or else a midpoint of this wire over here, and here let me just consider a two small pair of elements, say element P1 and P2, which are at equal distance from this reference point. And here suppose I am interested in calculating the electric field at the point P, which is at a distance of small r from this wire. In that case, the electric field due to this element P1 at the point P will be something like this. So this is the direction of the electric field, okay, due to this element. In the same way, the electric field due to this particular charged element, I'll say, it will be pointing in this direction. Now here you see one vector E1 pointing in this direction, vector E2 pointing in an upward direction. So here if you just want to know the net electric field at the point P, you can apply the law of parallelogram and you can easily get it. So here when you apply the law of parallelogram, that will give you the direction of the electric field something like this. So that's the direction of the electric field. Or I can say that here the direction of the electric field is pointing radially outward, okay. Or even if you just work with a different pairs of elements of the same wire, in that case also the direction of the electric field at any point, if you just calculate over here, anywhere in the space, in that case you will be getting the electric field to be pointing radially outward. Or if you want to see the field lines in three-dimensional space, in that case what you can do, you can just take this radial vector which is OP and rotate it around this wire. So that will give you the direction of the electric field lines in a 3D space, and it will look this something like this. So this is the field lines what you will see. Now here what you see is the field lines are pointing outwards, which means that the charge available on the wire are my positive charge. In case if you have a negative charge, in that case the field lines will be pointing inwards. So that is about the direction. Now here what you see, these field lines, this is in a one plane which whose center is exactly at the origin. In the same field lines will continue for the rest of the length of this wire, okay. Or in general I can say that the electric field lines are radial in nature, okay, and it will be pointing outwards if you have a positive charge, or inward if you have a negative charge. Now here if you just try to calculate the magnitude of the electric field at anywhere, okay, in the space surrounding this wire, in that case what I can say is that just because it is showing a radial nature of the field lines, in that case, okay, if I just want to calculate a point P over here, electric field, in that case I can just say that the magnitude of the electric field will always depend upon the radial distance, okay. In the same way, if you just try to calculate here, it will be again depend upon the radial distance, just because of the radial nature of the field lines. So here we are interested in getting an expression, okay, to calculate the magnitude of the electric field. So what we have seen is a direction of the electric field. So now let's apply the Gauss theorem and get an equation to calculate the magnitude of the electric field, okay, for this at any point from this wire. So to apply the Gauss theorem, okay, we have the expression when you see the Gauss law, I'll say. So here we are having the Gauss law I can say a Gauss law, which we know is phi of E is equal to 1 over epsilon naught times the charge enclosed by the Gaussian surface. So this is the Gauss law. So now let me bring a Gaussian surface into the picture. So here I'll be considering a cylindrical Gaussian surface whose radius is small r, and let L be the length of this Gaussian surface, and here the axis of this Gaussian surface is exactly along the line of charge. So this is how the Gaussian surface has been put up. Now when I see the Gaussian surface, okay, I see that there are total 3 surfaces. One is your curved surface. Let me call this as my S1. Let S2 be the top face of that cylindrical Gaussian surface, and S3 is a bottom flat surface. So here I need to calculate the electric flux first of all from each of the surfaces. So here, just to test the electric flux, let me just take a very small area element of each of the surfaces. So here I'll be considering ds1 as my small area element for the curved surface, the ds2 for the top surface, and the ds3 for the bottom surface. Now here we have equation to calculate the electric flux. So the electric flux, I can say electric flux, which is phi of E is equal to vector E dot vector ds. So that's the expression, and the same dot product I can write it in terms of E dot ds into cos of theta. So this is the formula that we know. Now here we are having 3 surfaces for the cylindrical Gaussian surface. So let me rewrite this formula for all these surfaces individually. So here in this case, when I say that the phi of E will be equal to vector E dot vector ds1 plus, okay, it will be vector E dot vector ds2 and plus vector E dot vector ds3. So for all the 3 surfaces. Now this formula is for a small planar area element, but we are interested in getting the electric flux through the entire surface of the cylindrical surface. So in that case, I need to put up an integral sign, the area integral along the x1, the area integral of the S2, the surface S2, and the integral of the S3. So that will give me the net flux passing through the the entire surface of the cylinder. So here, if I just use this, the dot product of vector E dot vector ds1, here in this case I can just take the electric field over here. This will be a E1 E dot ds1 into cos of theta. So when you see, the theta is the angle between the unit vector of this planar area element and the electric field. So here, this is my planar area of the surface S1, and if you just see the n cap, okay, of this planar area element, it is pointing in the same direction as of the electric field of this wire. So the angle between them, I can take it as a 0. So cos of 0 plus, I can say this is my integral of S2 E dot ds2, again cos of theta. This time if you just see, this is the top planar area element, and here if you just draw an n cap, okay, for this planar area element, a unit vector which is pointing upward like this, and the electric field is my radial electric field, right? So that's forming a 90 degree over here. So in this case it will be a 90, and the same for the S3, it will be the electric field dot ds3 into cos of 90, which is again it will be a something like this. N cap is pointing downward, and that's the direction of the electric field, so 90. So here when you solve this, I'll be getting phi of E will be equal to, here I'll be getting E is my constant, so I'll be taking it out, E, and it will be integral of S1 ds1, cos of 0 is how much? 1, so this is my ds of 1. In the same way, this is what? Cos of 90 is how much? 0, cos of 90 is 0, so both the terms will go to 0. So what you are left with is this expression. So here I can just say that the phi of E, I can just rewrite this phi of E will be equal to E into this integral of S1 into along the surface area element S1. I can just write, this is a very small planar area element of this surface, curved surface. So we are interested in the flux through the entire curved surface. So in that case, I can just replace this integral of S1 into ds1 by the area of this curved surface, which is nothing but 2 pi r into L. So here I have got the phi of E. Okay, that's an electric flux I have got. So we have got the expression for this. Now here, what I again know is that the linear, if you just see the linear, I consider the linear charge density, right? So this is my linear charge density, which is nothing but my lambda, which is equal to the charge per unit length. So this is what we know. So here we are interested, this Q over here is the charge enclosed by the Gaussian surface, correct? So I can just rearrange this and I can say that the charge enclosed by the Gaussian surface is nothing but a Q, I'll say a Q is equal to lambda into L. So this is my second expression. So I have got this, the charge enclosed by the Gaussian surface. Let this be my first, this is my second equation. And now what I'll do is that I'll substitute this equation 1 and equation 2 in this Gauss law. So the left hand side, I can write this. So the left hand side, what I am getting is E into 2 pi RL, which is equal to Q is the charge enclosed by the Gaussian surface. That is my lambda into L upon epsilon naught. And here the lambda and lambda will, L and L will get cancelled. So if I just rearrange this expression, okay, what I'll be getting, the electric field is E is equal to lambda upon 2 pi epsilon naught into the R. So this is the magnitude of the electric field. This is the magnitude of the electric field. Now, if you want to write the same electric field in a vector form, what we know is that the direction of the electric field is always radial. So in that case, I can just rewrite this as the electric field over here. I can say that the vector form of this will be equal to lambda upon 2 pi epsilon naught into the R along the n cap, where n cap is the unit vector of a radial. So this is the vector form that you can write it. So which is n cap is the unit vector of your radial field. So this is the expression that what we have got. Now when you see this expression, okay, as I said, the magnitude of the electric field will always depend on the radial distance. So here R is your radial distance, okay, or you can say that the electric field is inversely proportional to the R. Now here an important point to make a note is that while deriving this equation, what we have considered is a charge of the wire which is enclosed by the Gaussian surface and not the charges which are outside the Gaussian surface, but the electric field, what you are getting over here is due to the entire charge of this wire. So that's the first point. The second point here is that we have considered the length of this wire to be infinite, which allows us in considering the direction of the electric field to be exactly normal, with this curved cylindrical surface. So that's the second thing. And the third thing is that here I can make a use of the same expression even to calculate the electric field, at the central portion for a long finite wire, wherein I can just ignore, the end effects, of that long wire. So here I can also make a use of this equation for that case as well. Now these are the few points that you need to make a note. Okay. Now let's see another case when you have a uniformly charged infinite plane sheet. Now here this is a thin infinite plane sheet which is having a uniform surface charge density, say sigma, and here again let us consider this sigma to be a positive, which means that the charges available on this plane sheet are my positive charges. Now here if you just want to know the direction of the field lines, okay, of this particular plane sheet, what I know is that for any charged surface the direction of the field lines are exactly normal with the surface area. So in that case, you will be getting the field lines to be something like this. So this is the direction of the field lines on both the sides of the plane sheet. Now here if you just try to calculate the magnitude of the electric field, at some equal distance, on both the sides of this plane sheet, okay, you will be getting the same magnitude, of the electric field. So now here this is about the field lines for this particular case. So here we are interested in measuring the electric field in a space, surrounding this particular plane sheet. So we are going to again apply the Gauss theorem. Okay, so let me write the Gauss theorem. We have a Gauss theorem. Gauss theorem, which is phi of E is equal to the charge enclosed by the Gaussian surface by the epsilon naught. So let me just put it once again, this is as equation 1. So here to calculate the left hand side of this equation, let me bring a Gaussian surface back into the picture. So here let me consider again the same cylindrical Gaussian surface, which is like this, and here let A be the cross sectional area of this cylindrical Gaussian surface, and this time let me consider the 2r has a length of this Gaussian surface. Even you can consider the L. Okay, so this is the entire length of my cylindrical Gaussian surface, alright, or else from this point O till this point P you are going to get r, so that's small r, and here it's an equal distance, so r plus r, that will give 2r. Alright, so now again let me call this as my surface S1, which is my curved surface, S2 be this left flat surface, and let S3 be the right flat surface of this cylinder. So here we are interested in getting the flux. Okay, so let me write the electric flux through this entire cylindrical surface. Okay, so I can write this as my E dot ds into the cos theta. So this is the expression to calculate the electric flux. So here I see that the cylindrical surface has got 3 surfaces. Okay, so let me rewrite this same expression as S1, which is my curved surface, E into ds cos theta, plus integral of S2 into E into let me choose this. These are my small planar area element of each of the surfaces. Okay, so this is plus integral of, here it's a cos theta, plus integral of S3 into E dot ds3 and cos of theta. So that's the expression. Now let's see the first integral. So here, let ds1 be a small planar area element of the curved surface. So when I choose this small area element, let's say here, in this case, the unit vector of this planar area element will be pointing, in a upward, right? Or else outward, I'll say. And here the electric field lines are exactly pointing towards right. Yes, so they are forming the angle between this n cap and the electric field is exactly a 90 degree. So here the cos of theta is what? You are getting the S of 1 into E dot ds1, and this is cos of 90. So plus this integral, which is my S2 over here, the unit vector is pointing towards the left, electric field direction is also pointing towards the left, both are parallel, so theta is equal to 0. So I can say S2 will be equal to E dot ds2 into cos of 0 plus integral of S3 E into ds3, and here again cos theta, both the unit vector and the electric fields are pointing towards the right and both are parallel, so in that case the cos theta will be 0. So here what I'll get, the phi of E, the cos of 90 is what? 0. So it will be a 0. I can just write this is 0 plus electric field E here will be a constant, correct? So E is a constant, and I can just take this out. It will be a S2 into ds2, and this cos of 0 is 1. In the same way, this is electric field. I can take it out. Here it will be S3 into ds3, cos of 0 is 1. All right. So the phi, what I'll be getting here is electric field E into integral, the surface integral of this particular surface area. This is my S2. Yes, and I consider the cross-sectional area of this Gaussian surface to be A. All right. So here let me just write the A be the cross-sectional area, of this Gaussian surface. So in that case, I'll be getting this as my A. So here in the same way, it's the same thing for the integral, S3. I can just write it as again E dot, E into A. So which is my phi of E will be equal to twice the E A. So that's my second equation what I have got. So this is the electric flux, which is for this cylindrical Gaussian surface. Now here this Q is again the charge enclosed by the Gaussian surface. So let me solve for that. Here I am having the charge enclosed. What I said that this plane sheet is having a surface charge density. So we are having a surface charge density, which is nothing but a sigma. And how we write the sigma? Sigma is nothing but a charge per unit area. So that will give me a surface charge density. So I'm interested in the Q. I can just rearrange this Q, which is enclosed by this Gaussian surface, correct? So this is the surface. So I can just say that the charge enclosed by Gaussian surface is my Q. Okay, Q is nothing but sigma into the A. So that's my second equation. Now what I do, I just substitute these equations. Let me just substitute equation 1 and 2 or 2 and 3 in equation 1. So on the left hand side, I can just write this 2EA. So and I'll be getting the twice the electric field into the cross-sectional area is equal to sigma times the A, where sigma is your surface charge density, correct? And here what I'll be getting is on the right hand side I have an epsilon naught, which is this epsilon naught. Here the area and area will get cancelled. So what I am left with is the electric field E is equal to sigma upon twice the epsilon naught. So this is the magnitude of the electric field, for any point, on both the side of this thin planar sheet. Now, if you just want to write it in the vector form, I can just say that the vector form over here, I can just write the vector form. I can just say vector E will be equal to sigma upon twice the epsilon naught into the n cap, where n cap, is the unit vector, which is exactly normal with the plane of this Gaussian surface. Correct? That's the n cap. So this is the vector form for your electric field. Now, when I see this equation, what I can say is that here the electric field is independent of the r, okay, which is the distance, from this thin planar sheet. The next thing is that here the sigma, if suppose the sigma is positive, in that case the electric field lines will be pointing outward, and if the sigma is negative, in that case the electric field lines will be pointing towards this thin planar sheet. So that is about the direction. So this is the equation, to calculate the electric field in a space surrounding a thin infinite plane sheet. And the same expression, I can also use it, to calculate the electric field at the central portion, of some finite large, planar sheet, wherein I can just ignore, the age effect of that plane sheet. So that is the expression I can make a use. So now let's see the another case when you have a thin uniformly charged spherical shell. So here this is my thin spherical shell, which is having a uniform surface charge density, say sigma, and here again let us consider the sigma to be a positive, which means a positive charge available on this spherical shell. Here let us consider O to be the center of the spherical shell, and let capital R be the radius of this spherical shell. Now here, if you just want to know the direction of the field lines, from the properties of the field lines, we know that the electric field lines are always normal, to the charged surface area. So here, if I just draw, this is my thin spherical shell. So here in this case, if I just draw a normal, at this particular point, say, that will give me a direction of the electric field. In the same way, at this point, the direction of the electric field will be pointing towards the left, pointing towards the right, and down. Like that, in general, the field lines will look something like this. Now, here, this is a sign of what the field lines are in a radial, right? And here, if you just try to measure the magnitude of the electric field, at some equidistance, from say at a point O, if you just take some fixed distance, and if you just try to measure it in all possible direction around this spherical shell, you will be getting the same magnitude of the electric field, which means is that this particular case, is showing a spherical symmetry. Yes, so the field lines over here are radial and shows a spherical symmetry. That is all about the field lines. Now here we are interested in measuring the electric field, right? So here there can be three cases. One, the field outside the spherical shell, the field on the surface of the spherical shell, and the field inside the spherical shell. So that's the task. So here we are going to apply the Gauss theorem to calculate this electric field. So what I know is that let us consider the first case, that is a field outside the spherical shell. So let's go with the first case where you are having, I'll say, a field outside the spherical shell. So here let me consider a point P, okay, over here, which is at a distance, say small r from the center of this spherical shell, correct? So here I'm interested in measuring at this particular point the electric field, which is outside this spherical shell. So let me bring a Gaussian surface, into the picture. So here, let me consider a concentric sphere, has a Gaussian surface, which is like this, whose center is exactly coinciding with the center of the thin spherical shell. And let r be the, again, let small r be the radius, of that Gaussian surface. So you see that the Gaussian surface is passing through this point P because I'm interested at this particular point. So again, as I said, this thin spherical shell shows, spherical symmetry, correct? Which means is that again, this is the point P which is at a distance of small r. In the same way, if you just try to calculate at this particular point, you will be getting the same magnitude of the electric field. So let me write the Gauss law first. So what we know is the Gauss law states that the electric flux is equal to 1 by epsilon naught times the charge enclosed by that Gaussian surface. So let me put it a number 1. So this is the Gauss law. So here, let us work out with this left hand side first. So here the flux, we know the expression to calculate a flux, electric flux, is nothing but here in this case, let me write a surface integral into E dot ds into cos theta. So I'm writing it directly. Vector E dot ds can be written as E dot ds cos theta. Correct? Now let us see what the theta is. Yes, this is a surface integral. So here if I just choose, a small area element like ds, let me choose it, somewhere here. Okay, so this is my small area element. Okay. Now if you just see the direction of the field lines, it's pointing upward. And if you just see the direction, okay, the unit vector of your planar area element, it's also pointing in the same direction. Correct? So which says that the theta, that here theta is nothing but it's an angle between the electric field and the unit vector of this surface area. Correct? In the same way, if I just take it here, you see the electric field is pointing towards the left, while the unit vector of your surface area is also pointing towards the left. So in general, it will be the same for all the points available on the surface, right? Gaussian surface. So here in that case, I can say the theta is equal to 0. Yes, or else the unit vector of this entire surface area, okay, with the electric field lines, are parallel. So in that case, I can just write this expression as phi of s, or else let me say the electric field over here is a constant, correct? So electric field E is constant. It's the same everywhere on that surface, Gaussian surface, and this is my surface integral into ds. Here the theta is 0, cos of 0 is 1. So this is the expression. Now I can just write this as E. What is a surface integral? Yes, here ds stands for a very small area element, but I am interested in for the entire surface, right, of the Gaussian surface. So what is the formula for this sphere? Yes, I'm interested in the surface of this sphere. So that sphere, I can just write it as 4 pi into r square. So that's the formula to get the surface area. So I have got the electric flux in this case. Now let me put it as expression 2, equation 2. So I have got the left hand side. Now here this Q, what we are talking is the charge which is enclosed, by this Gaussian surface, right? Or else here this charge Q, is available, on the thin spherical shell, yes, which is enclosed by this Gaussian surface. So what we know is that I said that this thin spherical shell is having a uniform surface charge density. So I'm having a surface charge density, which is nothing but my sigma, I'll say. Let me just say a sigma over here. Sigma is equal to, that is charge Q per unit area. So this is how we measure the surface charge density, right? Charge per unit area. And this area, what I am talking about, is the area of the thin spherical shell. Okay, because the charge is available on this particular shell, correct? So in that case, I'm interested in area. Again, this is my sphere. So to calculate, the area, surface area of this thin spherical shell, the formula is 4 pi into the radius of that sphere. So here my radius is capital R. So I can say that the sigma is equal to Q by 4 pi capital R square. Here it's a capital R, this is a small r for the Gaussian surface. Okay, so I have got this. So I'm interested in the charge Q. So I can say that the charged enclosed by Gaussian surface is Q is equal to sigma into 4 pi R square. So this is equation 3. Let me mark this as equation 3. So I have got the electric flux. I have got the charge enclosed by the Gaussian surface. So let me substitute this equation 2 in equation 3. So here, when I substitute this, let me say substitute equation 1 and 2 and 3 in equation 1. So what I get, phi of E is what? E into, I can just say E into 4 pi R square, and the charge enclosed is how much? Sigma 4 pi R square. So here it is sigma 4 pi R square divided by epsilon naught. So here this 4 pi and the 4 pi will get cancelled. So what I am left with is, I can write it as E over here. The electric field E is sigma upon epsilon naught into R square by small r square. So this is the equation to make a note. So this is the electric field that will give the electric field at any point P which is lying outside the thin spherical shell. So let me mark this as the equation 4. So that's the expression. Now here the same expression, again, I can just I can write it in like this. Okay, here I can just write it. The same expression can be written as E is equal to, if you just want in the numerator, say a small q. Okay, and a small q is nothing but sigma into 4 pi r square. So here sigma and r square is available. So I'm interested in a 4 pi. If I just multiply this numerator with a 4 pi and a denominator with the 4 pi, what I'll be getting. Okay, I'm just multiplying numerator and denominator with the 4 pi, epsilon naught into the r square. So when I multiply over here in the numerator 4 pi, that will give me a 4 pi sigma r square, which I can write it as a small q. So this is the expression for that. So this is the magnitude of the electric field. Okay, I can again show it like this, where again important point to make a note, this q is nothing but sigma 4 pi r square. So that's the expression. And if you want to write it, in terms of a vector form, so I can write it the vector form of the same expression. I can just say that electric field vector E is equal to q by 4 pi epsilon naught into r square. Now here this r is a radius, correct, is the radius of the Gaussian surface. So which is pointing, outward, correct? So in that case, I can just write a unit vector of that radius, and I can just show it r cap. So this is the vector form. This is the vector form of your electric field. Now here, if the charge q is positive, then these field lines will be pointing outward. And in case if you have a charge to be negative, in that case the field lines will be pointing inwards. So that is about the direction of this electric field. Now here, if you just see this expression, okay, it's exactly the same equation what we have got when you just place a point charge in a space. Yes, it's the same thing, 1 upon 4 pi epsilon naught into q upon r square. So what I can say is that the field outside this charged thin spherical shell is as if the entire charge of this thin spherical shell is concentrated at origin O over here. So it's acting in that manner. Okay, so that is about the this electric field for the point outside the thin spherical shell. So here the field outside this charged thin spherical shell is acting as if the entire charge of this spherical is been concentrated at the center O. So looking at this relation, I can say. Now this was for the point P lying outside this thin spherical shell. Now let's see the another case. That's the second case when you have you are interested in measuring the electric field exactly on the surface of that thin spherical shell. So let's see the second case. Let's see the second case when field on this spherical shell. Field on the spherical shell. Okay, so here what I can just see do is that I can just consider this Gaussian surface to be exactly of same, I'll say of same radius as of a thin spherical shell, or else approximately close to that. You see that the Gaussian surface is enclosing this spherical shell. So when I just consider that, I'll just say let r small r be approximately close to the capital R. In that case, what you're going to change, this everything remains the same. What will change is that you can just replace this capital R or else a small r by this capital R. You can just do the replacing, and in that case when I just replace this, say small r is equal to capital R, so I'll be getting the same expression here. So I'll be just using the equation 4. So in equation 4 I'll be getting, so here just let me say this is the expression A. So when I substitute equation A in equation 4, okay, what I'll be getting is the electric field here. So the electric field will be what? I'm just replacing this by capital R. Capital R and capital R will get cancelled, and you are left with sigma by epsilon naught. So this is the case, okay, which is on the surface of this spherical shell. So this is the electric field. Or else if you want to show it in terms of this, you can just replace this small r by capital R. So in this case, I'll just write the vector form. E is equal to 1 upon 4 pi epsilon naught, okay, and this will be a charge q, and small r is replaced by a capital R. So let this be a capital R square, and I can just say that it is along the r cap. So this is the vector form of this. Okay, so that's the vector form. So this is the field on the surface of the spherical shell. Now a third case, let's try to calculate what will be the field inside this thin spherical shell. So here let me take this Gaussian surface inside this thin spherical shell. Let small r, so here let us consider one point. So let this be the point P where I'm interested in measuring the electric field, which is inside the spherical shell. So this is the Gaussian surface what I have drawn. Again, let small r be the radius of that Gaussian surface. So here when you try to calculate the third point, the field, I'll say field inside the spherical shell. Field inside the spherical shell. So again, phi of E is how much? So in this case, the phi of E is the charge electric field E into 4 pi r square. So here I'll say E into 4 pi r square. But on the right hand side, the charge enclosed by the Gaussian surface, here I don't see any charge enclosed by the Gaussian surface, correct? Because the charges are available on this thin spherical shell, correct? Yes, so in that case, the charge available which is enclosed by the Gaussian surface is 0, and this is epsilon naught. So here clearly I can say that the electric field here, what I am getting is E is equal to 0. So that's the important point. So here the electric field, what we are getting is 0. Why? Because you don't see any charge enclosed by the Gaussian surface. So here what I can say is that if we just try to calculate the field, inside this thin spherical shell at all the points, inside the shell, you will be getting to be 0. Okay, so these are the 3 different cases of this thin spherical shell. Now here in this question, we are given 2 infinite parallel planes which is having a uniform charge densities of sigma 1 and sigma 2, and here we are told to calculate the electric field at a point to the left of the sheet, between them, and to the right of the sheets. And here we are told to consider that sigma 1 is greater than sigma 2 and it's greater than 0. So which means that a positive charge available on both these 2 sheets. All right. So here what we know is the equation to calculate the electric field for the electric field at any point in a space surrounding the infinite plane sheet is, we know the expression that vector E is nothing but sigma upon twice the epsilon naught into the unit vector n cap, correct? So this is the main equation, I'll say, that I'll be using over here. Now first of all, let's see the direction of the electric field of both these sheets. So here the sheet 1, when I look at the sheet 1, the direction of this E1, okay, it will create an electric field towards in this direction. So let me write this as my vector E1. And the same thin plane sheet, is also going to have electric field, towards the right, or I'll just say this is my vector E1. And also the same field lines will be available in the region 3. So this is the direction of due to the sheet 1. So that's the direction of the electric field in the region 1, region 2, and region 3. In the same way, okay, I'm going to have, let me use a blue color. So here the electric field due to this sheet 2, I'll be having in this direction. So this is my vector E2, and in the region 2 it will be towards the left. So vector E2, and in the region 1. So that is, I can write it as a vector E2. So these are the directions of my vector E1 and a vector E2 in all these 3 regions. So here, if you want to know, let's go for the first case. In the region 1, if you want to know the net electric field, here what I can just do is, let's go with the first case. I can say that I can apply a superposition principle over here to calculate the net electric field. So I'll be getting vector E is equal to, vector E1 plus vector E2. And here, let me choose, r cap, has a unit vector. So here, this is my r cap. Let me choose this as my reference point. So r cap let this be my vector r, and here which I can write it as a r into the r cap, where r cap is my unit vector. All right, so the direction of the electric field, I'll be writing with respect to this unit vector, which is my r cap. So here I can just say that what is the direction of the electric field in E1? E1 is pointing towards a left. Left in a sense, the r cap, what I have chosen, is pointing towards the right. So this is my reference unit vector, I'll say. But the electric field is exactly opposite to this vector. So in that case, I have to write a minus. I'll be getting a minus of sigma upon twice the epsilon naught into the r cap. So that's the electric field of E1 plus the E2. Even E2 is pointing towards the left with respect to this. So I can just say the sigma upon the twice the epsilon naught into the r cap. All right, whereas the magnitude, we have this equation. Now I can just rearrange and write this expression as minus into, this is my sigma 1, sigma 2. All right, so I can just say that twice the epsilon naught, I can write a sigma 1 plus sigma 2 and along the r cap. So this is the equation, the net electric field in the region 1. So twice the epsilon naught, so the electric field in the region 1. So that's the expression. In the same way, I can also calculate in the region 2. In the region 2, again, vector E in the region 2, I'll be getting the electric E1 is in the same direction as of this, while the vector E2 is opposite. So the first vector E1, I'll say it will be positive sigma upon twice the epsilon naught along the r cap minus the addition of this E2 is opposite of that. So it will be a minus sigma by 2 epsilon naught along the r cap. So which I can write it as, which I can show is equal to, I can just say that again sigma 1 and sigma 2, sigma 1 minus sigma 2 divided by twice the epsilon naught into the r cap. So that's the net electric field available in the middle section. And for the third case, I can say vector E in a third region is, I see that the electric field E1 is pointing towards the right, electric field E2 is also pointing towards the right. So I'll be getting the surface density of the plate 1, sigma 1, divided by 2 epsilon naught along the r cap plus sigma 2 by twice the epsilon naught and the r cap. And here I can just add this and I can get sigma 1 plus sigma 2 by twice the epsilon naught, okay, into the r cap. So these are the equations of the net electric field in the region 1. This is the net electric field in the region 2, and a net electric field in the region 3. So that's the answer for this particular case. So here again I'm having two infinite parallel planes which are having a uniform surface charge densities, but this time the charge available on each of the sheets are my equal and opposite charges. So that is a positive sigma for your sheet 1 and a negative sigma for your sheet 2. So here we are interested in measuring the net electric field due to this both the sheets in the region 1, region 2 and the region 3. So here let me again consider the vector r1 as my reference vector. So this is my vector r, and which I can write it as a magnitude of r into the r cap. So r cap is my unit vector. So here this is my positive charged plane. All right. So in that case, the electric field lines, if I just want to show here, it will be pointing outward on the left side. So this is my vector E1. In the same way, it will be pointing towards the right and outward. So this is my vector E1 again. And some field lines in the vector in a region 3. Yes, so this is the direction of the field lines in all the 3 regions. Now let's see what will be the direction of the field lines due to this negatively charged plane. So here, if you want to draw the field lines in the region 3, it is a negatively charged plate. So that means the field lines should be pointing towards the plane, correct? So this is the direction I'll just give. So this is the direction of the electric field lines. So let me write this as my vector E2, that's a towards the plane because of the negative charge. In the same way, in the region 2, it will be pointing towards the plate. So that is my vector E2. And here as well, it will be towards the plane. So this is my vector E1. So these are the direction of the field lines due to this plane 2. Now let's go with the first region. Okay, so let's see the first region. I'll say a region 1. Okay, so what I do is I'm having a net electric field in the region 1. Okay, it's nothing but the addition of the electric field E1 and the electric field E2. So I have the equation to calculate the electric field, the magnitude of the electric field, which is my E is equal to sigma upon twice the epsilon naught. So this is the expression, the magnitude. So I'll be writing the sigma upon twice the epsilon naught of this electric field E1, and it's pointing towards the left. This is towards the right. So a minus into r cap. Correct? Now the addition of E2, it's pointing towards the right, and even this my reference vector is pointing towards the right. So it will be a positive sigma by twice the epsilon naught into the r cap. Now here, if you just see this, the electric field in the region 1, what I'll be getting is 0. So that's the electric field in the region 1. And you can, looking at this direction as well, you can directly say that it's a pointing towards the left, pointing towards the right. And here in this case, the sigma, the surface charge densities are same, right? Equal. So in that case, it will exactly cancel out. So let's go for this region 2. In the region 2, the electric field in the region 2 is equal to, the E1 is pointing towards the right, is the same direction. So I can write this as my positive charge, sigma upon twice the epsilon naught into the r cap along the same direction as of r cap. E2 is also pointing towards the right. My r cap is towards the right. So it's a sigma by twice the epsilon naught into the r cap. And I can just add this. When I add this, what I'll be getting is sigma upon epsilon naught into the r cap. So that's the electric field, the net electric field available in this middle region. And for the third region, I can just say in the region 3, the vector E in a 3 will be equal to what? E1 is towards the right. So it will be minus sigma upon twice the epsilon naught into the r cap. And yes, here this is exactly opposite, and that will be my minus. So here it's a positive because E1 is pointing towards the right and the r cap is also towards the right. So the electric field due to this sheet 1 in the region 3 is my positive, and the electric field due to the sheet 2 in this region, okay, I'm having a negative because it's exactly opposite, and that will give me a sigma upon twice the epsilon into the r cap, and they're equal and opposite, so that will give me a 0. So these are the electric fields in the region 1, region 2, region 1, region 2, and region 3. So these are the electric field lines. Now if you just see this particular case, here the sheet 1 and sheet 2 are having exactly equal and opposite charges, all right, And if you just see the electric field, what you are getting in the region 2 is this sigma by epsilon naught into the r cap, right? So that's the electric field available, between this two plates. While the electric field, outside this both the plates, are 0, which is this. So this particular setup, is basically used, to get a uniform electric field. So here in this case, in general, if I just want to show the direction of the field lines will be from positive towards the negative. So this is the direction, you will see of the field lines. So this such type of setup is used, to get a uniform electric field. Looking at this value, yes, you can see that it will be a uniform electric field. So that's the answer for the question. So things to remember from this today's session is the techniques used in getting an expression for electric field due to a system of symmetrical charge configuration with the help of a Gauss law. And here, these are the few expressions that we have derived in this today's session. So here, the expression 1, gives you the electric field in a space surrounding an infinitely long straight wire, which is having a uniform linear charge density. The expression 2 can be used to calculate the electric field when you have an infinitely large plane sheet. So that's the expression. While these expressions, are for your uniformly charged thin spherical shell. When you calculate the electric field outside the spherical shell, you can make a use of this expression on the surface of the spherical shell, and inside the thin spherical shell, what we know is that the electric field is 0 because the charges are available on the outer surface of that thin spherical shell. So that's the reason. Now here, suppose if I just want to show the graphical representation, of all these three different cases, in terms of E versus R, okay, I can show it, something like this. So here you see that for the first case, the electric field falls as, 1 over R, where R is a distance at which you measure, the electric field from the wire. So that's the graph. In the second case, I see that the expression is independent of the R, correct? So in this case, the electric field will be a constant. And in the third case, we know that up till the R, okay, the electric field inside the spherical shell is 0. But on the surface of the spherical shell, you will be getting an electric field, which is this. So that's the electric field. And as you start measuring the electric field outside the spherical shell, it will fall as a 1 over R square. So that's the graphical representation of E versus R. So these are the few points that you need to make a note from this today's session. Thank you very much.